Welcome to your Lesson 10-2 podcast, Mean and Standard Deviation of a Binomial Distribution. So yesterday we took a look at certain binomial situations and their distributions, okay? And then also what happened to those distributions as you change the number of trials and you change the probabilities, okay? So when we talk about mean and standard deviation, a couple things I want you to remember is how we calculated the mean of a distribution, okay? Which was basically what we called expected value. Expected value was a theoretical mean or a theoretical average for a situation. Okay. And then standard deviation was a measure of spread. Okay. How wide the data set was, or on average, how far each piece of data was from the mean. So please do not forget back from like chapter 1 how to calculate means and standard deviations. Okay, but the situation we're going to look at today is one more binomial one where we have the Professional Darts League. The throwers are real athletes. They can hit the bullseye 80% of the time under any conditions. Suppose that Niles sharpshooter, known as Triple 20, takes 3 shots at the bullseye. How many can you expect him to make? So what I want is how many can I expect him to make is I want a theoretical average. Okay, theoretically, what would I expect him to do? So I'm going to do a expected value calculation. Okay, the number of trials is 3. The probability of success is 0.8. Okay, probability of failure is 0.2 if you want that down. And basically, I want every possible probability if I'm going to do the expected value. So my k values, or my x values, go from 0 to 3. So if I want to do this expected value, I'm going to make myself a little table. 0, 1, 2, and 3 are my possible outcomes. And to get their probabilities, I'm just going to use my calculator. I'm going to use, it's a binomial probability. So if I do this with my calculator, I'm going to do binomial PDF of 3 comma 0.8. And then you can get your calculator to give you these probabilities rather than you using the formula by hand. So this is 0.008, 0.096, 0.384, and 0.512. So these are the probabilities for the situation. Now if I want the expected value, do the expected value calculation. 0 times 0.008 plus 1 times 0.096 plus 2 times 0.384 plus 3 times 0.512. Okay, and what you'll find is this quantity is 2.4, which, if you look back at the situation, is a little obvious. Okay, 2.4 is just 80% of 3. Okay, and yes, this value can be a decimal. It's a theoretical average. Averages can have decimal values. Okay, but an easier way to do this calculation is basically just take the number of trials times 0.8. And this will be true whenever it's a binomial distribution or a binomial situation. Okay, so mean of a binomial distribution. We abbreviate it with the Greek letter mu. And all we have to do is take the number of trials times the probability of success and multiply them together. Okay, so that's the mean of a binomial distribution. So again, you don't have to go back and make this chart now. Okay, if it's a binomial situation and you want the theoretical average or the mean, okay, you can calculate mu equals n times p. All right, which if I have a mean, I should also be able to find a standard deviation. And there is another just simple formula for that. So notice I give you two things here. Okay, standard deviation is square root of n times p times q, and then variance is just n times p times q. We talked about both of those back in chapter 1. Now, this letter here, okay, is the Greek letter sigma. Well, we've heard about sigma before. The uppercase sigma is a summation notation. The lowercase sigma is standard deviation. Okay, basically sigma is the Greek letter kind of for S. So when we want to label things that start with S, you'll often see them using sigma. It's the uppercase for summation notation, the lowercase for standard deviation. And then remember, variance back from chapter 1 was just standard deviation squared. So the notation I use for it is sigma squared. And then that formula would just be n times p times q. Okay, so make sure you know that these two formulas. Okay, so what I can do now is I can go back to Niles if I want. Okay, and I can figure out, obviously, his theoretical average was 3 times 0.8, which is 2.4, but I could also calculate his standard deviation, square root of 3 times 0.8 times 0.2, and I can also calculate his variance, which is just 3 times 0.8 times 0.2. And these answers just end up being 0.693 and 0.480. Okay, so what we're saying is with that standard deviation, that sigma, is that on average he's about 0.693 away from the mean of 2.4. Okay, now a couple of big things you should understand about this. Okay, what we're calculating today are theoretical values. Okay, expected value, the mu, and the little sigma, the standard deviation we were doing our calculations for today, are theoretical values, where if you just if you add up the number of values and divide by the number of terms you have, or if you do our standard deviation calculation back from chapter 1, those are called sample values. Those are based on the actual data. Okay, so we call these sample means and standard deviations. Over here, we call them population means and standard deviations because they're more theoretical, where the ones we were calculating before are more sample ones. Okay, so for instance, if I give you a situation like this, you should be able to calculate the mean and the standard deviation for something like this. So notice probability that a newborn child will be female is about 0.48, and actually, it's not exactly 50-50. It's very close to 50-50, the probability of having a boy or a girl, but not perfectly. If you have 250 births a year, what's the expected number of females? Just mu equals 2,500 times 0.48. Okay, and then the standard deviation will be the square root of 2,500 times 0.48 times 0.52. And if I want the variance, I'm just not going to square root that number. 2,500 times 0.48 times 0.52. So just like Niles, okay? And your values that you get here are 1,200, 24.97, and then 624. Something like that. All right? All right, now the last example that we'll just mention real quick is it's just kind of a little application, a little problem-solving problem based on the formulas I just gave you. So if a binomial experiment has a mean of 50 and a standard deviation of 3, let's find the number of trials and find the probability of success. So what I want to solve for is n and p. Okay. Now, if they give you the mean of 50 and a standard deviation of 3, that's all we really know about the situation. So one thing you might want to do is use our formulas and write out the mean in terms of the formula. Use kind of a number sentence here. So mean is 50. So I know that 50 equals n times p. They tell me standard deviation is 3. So I know 3 equals the square root of npq. And now what I have here is I have a system, okay, and we have methods for solving systems, okay. So what I can do is I can basically use substitution. I'm going to put 50 in for n times p. Okay, and then you could solve for q. Now, granted, q is not one of the ones I'm looking for, but it'll help me. So I'm going to have 9 equals 50q. So q equals 9 over 50. That's my probability of failure. And if you remember, the probability of failure and the probability of success should always add up to 1. So technically there's another formula on here, but it's one you might just do in your head anyway. So I know that my p-value is 41 over 50. And if I have that, I can solve for n, because I can go back and use that original formula. 50 equals n times 41 over 50. And what we find out is your n is approximately 61. Because n is a number of trials, it should be an integer. So I'm going to just round to the nearest integer, which is 61. So there's my number of trials. There's my probability of success. So that's your podcast for lesson 10.2. And we'll see you next time.